The universe does not ease you into its horrors. It throws you into them without warning, without light, without mercy. And nowhere is that more obvious than on worlds where night never ends. Take T-R-E-S-2b, a planet where darkness is not a phase, not a cycle, but a permanent condition. There are no stars glittering overhead, no comforting points of reference in the sky. The blackness is absolute, thick, almost tangible, as if light itself is afraid to exist here. This is not the kind of night humans romanticize. It is suffocating. High Trace 2b is a gas giant roughly 1.5 times more massive than Jupiter. Yet what truly makes it terrifying is not its size, but its appetite for light. Its atmosphere absorbs illumination more efficiently than charcoal. Photons arrive and simply vanish, swallowed whole. Some scientists suspect the planet glows faintly in a deep, hellish red, not from reflected starlight, but from its own burning air, heated to temperatures comparable to fresh lava. Even if you could see it, the glow would offer no comfort. It would only confirm that the planet itself is on fire. Trace 2b resides in the 55 Cancri star system, a place that seems determined to showcase every possible way a planet can suffer. 5 worlds orbit this star, 4 of them gas giants reminiscent of Jupiter or Saturn. But the 5th, closer than all the others, breaks the pattern in the worst way imaginable. 55 Cancri E is locked in a gravitational embrace so tight that escape is impossible. One side of the planet is forever facing its star, baked relentlessly until its surface becomes a global ocean of molten lava. Seas of glowing rock churn and shift, not slowly like magma chambers on Earth, but violently, exposed directly to stellar fury. The other side never sees the sun at all. It exists in eternal darkness, frozen not by cold alone but by the absence of energy itself. Between these two extremes lies a narrow twilight zone, a thin, unstable strip where temperatures and conditions fluctuate violently. It is neither safe nor stable. It is a borderland between fire and void, where nothing can settle for long before being destroyed by one side or the other. If 55 Cancri E feels like a planet split by cruelty, HD 189733b feels like one designed to deceive. From a distance, it looks beautiful. Deep blues and whites swirling together like a cosmic marble. But this beauty is a lie. Those colors come from microscopic silicate particles suspended in the atmosphere. In simpler terms, glass. Here, the sky does not rain water or ice. It rains shards of molten glass. Worse still, the winds on this planet reach speeds of over 5,400 miles per hour, nearly Mach 7. On Earth, the fastest winds ever recorded barely reached 254 miles per hour. On HD 189733b, glass does not fall downward. It is hurled sideways at hypersonic speeds, scouring the planet's atmosphere and shredding anything unfortunate enough to exist within it. There is no shelter. There is no safe direction to face. The air itself is a weapon. Some star systems do not merely punish their planets, they erase them. In one such system, whose name is almost unpronounceable, 3 exoplanets orbit not a normal star, but a pulsar, the rapidly spinning core left behind after a star explodes. This stellar corpse rotates thousands of times per second, emitting beams of electromagnetic radiation, so intense they slice through space like cosmic blades. Every rotation strips a little more matter from the planets caught in its path. Atom by atom, these worlds are being eaten alive. They are not stable orbits. They are countdowns. Eventually, nothing will remain but scattered debris and fading memory. Then there is Kepler 70, once a hot blue dwarf star, now bloated into a red giant. When it expanded, it swallowed its own planets. One of them, Kepler 70b, survived the initial engulfment, but survival came at a cost. The planet was transformed from a Jupiter-like gas giant into a blazing rocky remnant. Its temperature now exceeds that of the sun's surface. The planet is literally hotter than the star that once consumed it. But this is not a victory. It is a delay. Kepler 70b is evaporating, its material slowly bleeding into space. Its continued existence is temporary, measured in cosmic moments rather than ages. Some planets are not destroyed in bursts of violence, but through slow, inevitable theft. WASP 12b is one of them. This gas giant orbits so close to its star that the star's gravity is actively pulling the planet apart. The atmosphere is stretched into a long, glowing tail, giving the planet the shape of a cosmic egg being torn open. WASP 12b cannot resist, cannot fight back. Over the next 10 million years, it will be fully consumed, stripped layer by layer until nothing remains. It is not exploding. It is being digested. Other worlds defy logic entirely. On LHS 436b, you would experience something no human mind evolved to comprehend. Burning ice. The planet orbits extremely close to its star, with temperatures hotter than a blazing oven. Yet its surface is covered in ice that does not melt. The immense gravity compresses the ice into an exotic, ultra-dense form that remains solid even under extreme heat. Step onto this world and you would stand on ice that sears instead of cools, a surface that violates every instinct you have ever trusted. No catalog of hostile planets would be complete without mentioning Venus, Earth's so-called twin. But the resemblance ends quickly. Venus's atmosphere is so thick that it traps heat with brutal efficiency, making its surface hotter than Mercury's despite being farther from the sun. Volcanoes constantly reshape the landscape. The clouds above are not water vapor, but sulfuric acid, condensing and raining down onto an already infernal surface. Even attempting to descend through the atmosphere would likely be impossible. The winds there rival Earth's most violent hurricanes, and the pressure would crush most spacecraft long before they reach the ground. And still, the universe finds new ways to unsettle. There exists a planet orbiting a small, cool red dwarf where temperatures plunge to nearly -370 degrees Fahrenheit, only marginally warmer than absolute zero. Light barely reaches it. Heat barely exists. The surface is locked beneath eternal ice that never thaws. And yet, if the planet has a rocky core, internal heat might exist far below the frozen shell. In that hidden darkness, under miles of ice, something unknown could be waiting. Far away, roughly 50 light-years from Earth, lies Dimidium, a tidally locked gas giant. One side faces its star forever, heated to over 1,800 degrees, blasted by winds exceeding 600 miles per hour. Iron within its atmosphere melts, vaporizes, then condenses and falls as rain, not water but molten metal. An endless storm of liquid iron pours from the sky. On Osiris, oxygen, normally a hopeful sign, becomes meaningless. The planet orbits so close to its star that anything capable of burning does exactly that. Its year lasts just 3.5 Earth days. The atmosphere is constantly being stripped away, blown into space like smoke from a dying fire. Then there are worlds where gravity alone is the killer. KLT9b, often mispronounced or misremembered because of its sheer extremity, is not the hottest, nor the coldest, but its density makes it lethal in a quieter way. A gas giant 20 times denser than Jupiter, its gravity would crush anything instantly. Standing there would not be dramatic. There would be no time to react. The atmosphere itself would become a collapsing weight, ending you before you could understand what was happening. And still worse is Kepler 7b, where temperatures exceed 4,000 degrees. Rocks boil, stone evaporates, rises into the air, cools, and falls again as a rain of molten minerals. Scientists believe it may once have been a gas giant, its atmosphere completely burned away, leaving behind only a tortured core. Not all threats are tied to stars at all. OTS 44 is a rogue planet, drifting alone through space, 11 times more massive than Jupiter. It is not bound to any star. It does not orbit. It wanders. If it collided with another planet, it would annihilate it without slowing down. And scientists are certain OTS 44 is not unique. There may be millions of such silent destroyers moving unseen through the galaxy. And as if that were not enough, theory predicts the existence of carbon planets, worlds where oxygen reacts with carbon to form toxic black clouds of CO2, oceans of tar, geysers of methane, rain composed of gasoline and liquid asphalt, igniting on impact. These planets are not confirmed yet, but physics allows them. And in this universe, allowance often becomes reality. At this point, the cosmos seems relentlessly hostile. But the darkness is not finished yet, because somewhere out there are worlds covered not in fire, not in glass, not in iron, but in water. Endless water. And that is where the fear changes shape. Imagine this instead. You are floating in the middle of an ocean that never ends. There is no shore, no island, no landmark of any kind. The water stretches in every direction until it dissolves into thick gray fog. Above you, dense clouds smother the sky, hiding a dim, distant sun that barely seems real. You cannot tell whether it is day or night. Time loses meaning here. Sound feels muted, swallowed by the mist. You are completely alone. You try to dive. Minutes pass, then hours. Still no bottom. The pressure builds relentlessly, squeezing your body, crushing your thoughts. Even if you were invincible, even if your lungs never failed, you would never reach solid ground. This is not Earth's ocean. This is a water planet, and this is what terror looks like when it is quiet. Ocean planets are worlds made primarily of water, ice, and small amounts of rock. To understand how extreme they are, you need perspective. All the water on Earth, every ocean, sea, lake, river, glacier, and cloud, makes up just 0.025% of our planet's total volume. That is almost nothing. Now imagine a world where 40 to 60% of the entire planet is water. Not on the surface. The planet itself is water. On these worlds, ocean depths can exceed 60 miles. Earth's Mariana Trench, the deepest place we know, plunges only about 6 miles. Down there, pressure already reaches crushing levels. On water planets, pressure can soar to 20,000 Earth atmospheres. No known material, no known organism could withstand that force near the bottom. And yet the water keeps going. At such pressures, reality bends. Water behaves in ways that feel almost illegal. Beneath the liquid ocean forms a massive layer of something called hot ice. A strange, ultra-dense form of ice that does not melt even under extreme heat. It sits there like a solid barrier, separating the ocean above from whatever lies below. If there is rock beneath it, it may never interact with the water at all. The planet becomes layered like a nightmare. Steam, liquid, crushing depths, and then frozen solidity, all stacked on top of each other. For a long time, water planets were theoretical curiosities. Scientists talked about them, modeled them, argued about whether they could exist. Then, slowly, evidence began to emerge. The first serious candidate was Gliese 1214b. At first, it looked unremarkable, just a faint dot orbiting a small red dwarf star called Gliese 1214. The star itself is nothing special. 5 times smaller than our Sun, about 300 times dimmer. Under normal circumstances, it would barely earn a footnote in an astronomy textbook. But in 2009, scientists noticed something strange. The star had exactly one planet, and that planet made no sense. Gliese 1214b is about 2.5 times larger than Earth and roughly 6.5 times heavier. Under normal physics, that should make it a dense, rocky super-Earth or even a small gas giant. But its density was far too low. At the same time, it wasn't light enough to be made mostly of hydrogen and helium. Gravity on its surface was eerily similar to Earth's. The numbers refused to cooperate until only one explanation remained. Water. Vast quantities of it. Steam. Oceans stacked on oceans. And just like that, humanity had its first true ocean planet. Or at least that's what the math said. In reality, Gliese 1214b has been frustratingly elusive. Scientists have searched its atmosphere for hydrogen, helium, water vapor, anything that might confirm its nature. They found nothing. No signatures. No clear clues. The reason? Its atmosphere is so thick and opaque that it hides everything beneath it perfectly. It is a planetary veil, a cosmic curtain pulled tight. Still, most researchers agree, Gliese 1214b is almost certainly a water world. It orbits shockingly close to its star, just 0.014 astronomical units away. For comparison, that is closer than the Moon is to Earth. A year there lasts only 36 hours. Temperatures swing between 250 and 535 degrees Fahrenheit. Hot enough to cook, but not quite hot enough to boil the oceans away. And that is where things become truly unsettling. On Gliese 1214b, there may be no clear boundary between atmosphere and ocean. Steam gradually thickens until it becomes liquid. Liquid slowly becomes dense enough to feel solid. You wouldn't splash into the sea, you would sink into it without realizing when air became water. Swimming would feel like descending into a boiling pressure cooker, surrounded by superheated mist and scalding currents. The ocean likely never ends, not in the way we understand endings. Eventually, you would reach the hot ice layer, potentially thousands of miles thick. Below that, a mystery sealed off by physics itself. Gliese 1214b is not alone. Another strong candidate is TOI 1452b, discovered nearly 100 light-years away in the Draco constellation. This planet is even more extreme, 7 times larger than Earth, 48 times heavier, and yet, again, far too low in density to be rocky. Scientists believe TOI 1452b may be almost entirely ocean. Unlike Gliese 1214b, this world may actually have a rocky surface beneath its water. That sounds comforting, until you remember what sits on top of it. An ocean so deep and heavy that the pressure near the bottom would make Earth's deepest trenches feel like shallow puddles. TOI 1452b orbits not one, but 2 red dwarf stars. Its distance from them is enormous, more than twice Pluto's distance from the Sun. Yet it completes an orbit in just 11 days, moving at staggering speed through space. How warm it is, how its ocean behaves, whether its water is liquid or supercritical, all of that remains unknown. Scientists hope the James Webb Space Telescope will eventually peel back its secrets. For now, it remains a looming question mark drifting in the dark. And of course, the question that refuses to stay quiet. Could there be life? Water is essential for life as we know it. These planets sit in their stars' habitable zones. On paper, they check the right boxes. But water alone is not enough. Life also needs minerals, chemical gradients, energy sources, ingredients that water planets may lack entirely. Many water worlds could be nothing but sterile, crushing oceans, sealed off from any rocky interaction. No nutrients, no chemistry, just endless, lifeless depth. But there are cracks in that pessimism. Meteorites and comets could deliver minerals over billions of years. Impacts could seed oceans with complex elements. And TOI 1452b, with its potential rocky core, might provide exactly the kind of environment where something small, simple, persistent could arise. Not civilizations, not cities, but bacteria, strange fish-like organisms, massive, slow-moving creatures adapted to darkness and pressure beyond imagination. It is unlikely, but not impossible, and that thin sliver of possibility is enough to keep scientists awake at night. Because so far, in the entire universe, we are certain of life in only one place, Earth. Whether that life is intelligent is debatable, but the search continues anyway. More than 4,000 exoplanets have already been discovered, and among them, some are not just Earth-like. Some may be better. That is where the story turns, away from nightmares, and toward something far more dangerous to our imagination. Hope. After everything you've seen so far, the burning skies, the crushing gravity, the endless oceans, it almost feels wrong to talk about better worlds. The universe has trained you to expect cruelty. And yet, quietly, almost shyly, astronomy delivers a twist. Planets that may not just tolerate life, but nurture it more gently than Earth ever has. NASA didn't compile this list to inspire poetry. They did it because the data forced them to. Among the thousands of known exoplanets, 24 worlds stood out, not because they were familiar, but because statistically, physically, they might offer more stable, more comfortable, and longer-lasting conditions than our own planet. These are called superhabitable planets, and the idea is unsettling in its own way. The first of these worlds carries a deliberately awkward name, KOI 5715.01. Scientists almost joke about it, let's be coy. But the planet itself is anything but playful. It orbits an orange dwarf star, and that detail matters more than it sounds. Our sun is a yellow dwarf. It's decent, reliable, but it's also impatient. In cosmic terms, it burns fast and will die relatively young. It has maybe 7 to 8 billion years left. Orange dwarfs, on the other hand, are patient giants of stability. They can live 45 to 70 billion years, long enough for life to form, fail, restart, and evolve complexity multiple times over. KOI 5715.01 sits comfortably within its star's habitable zone. A year there lasts about 190 Earth days. The planet is nearly twice the size of Earth, which means stronger gravity. That gravity does something subtle but powerful. It holds onto atmosphere more efficiently. Heat lingers. Air stays thick. Radiation is better absorbed and redistributed. The average temperature hovers around 52 degrees Fahrenheit, slightly cooler than Earth's average, but paradoxically more comfortable because the atmosphere traps warmth more evenly. No extreme cold nights. No brutal heat spikes. Just consistency. The downside? Distance. KOI 5715.01 lies roughly 3,000 light-years away. That's 18 quadrillion miles. There is no visiting it. Not soon. Not with any technology we can even sketch on paper. But distance doesn't make it less real. Then there's KOI 3010.01, a planet that feels almost suspiciously pleasant. Its average temperature is about 67 degrees Fahrenheit, warmer than Earth in exactly the way climate scientists consider ideal. Not hot enough to destabilize ecosystems, warm enough to accelerate biological processes. Its radius is about 1.5 times Earth's, again implying stronger gravity, thicker air, and better protection from cosmic radiation. Scientists suspect it has an atmosphere similar to Earth's, though its exact composition remains unknown. Water likely covers up to 60% of the surface, a more balanced distribution of land and sea than Earth's 70-30th split. More land means more chemical diversity, more coastlines, more shallow seas, more opportunities for life to experiment. And here's the part that makes scientists lean forward in their chairs. Based on everything we know, there's an estimated 84% chance of life existing there. Not intelligent life necessarily, but animals, ecosystems, food chains. If something walks there, it probably doesn't walk like us. Stronger gravity favors compact builds. Shorter limbs, sturdier frames, powerful muscles. Life there might look dense, grounded, and difficult to knock over. Less elegance, more resilience. And then there's Kepler 186f. This planet earned the nickname Earth's cousin. Not twin, not replacement, but family. It orbits a red dwarf star, smaller and dimmer than the sun. Red dwarfs live even longer than orange dwarfs, but they have a reputation for instability early in their lives. Kepler 186f survived that phase, which already says something about its resilience. The planet is roughly the same size as Earth. Its distance from its star places it squarely in the habitable zone. The sky there would look strange, bathed in a constant reddish hue, like an eternal sunset. Not dark, but unfamiliar. Beautiful in an unsettling way. What makes Kepler 186f especially compelling is its axial tilt, almost identical to Earth's. That means seasons. predictable climate cycles, stability over long periods of time. This detail cannot be overstated. Mars sits in our Sun's habitable zone too, yet its unstable tilt caused catastrophic climate shifts. Oceans evaporated, atmosphere escaped. Life, if it ever existed, lost its foothold. Kepler 186f avoids that fate. Its geometry supports longevity. The planet is about 490 light-years away. Far, but not absurdly so by galactic standards. Still unreachable. Still untouchable. Then come Kepler 62e and Kepler 62f, once considered the most Earth-like planets ever found. They orbit another red dwarf star in the constellation Lyra, about 1,200 light-years away. Kepler 62e is about 1.5 times larger than Earth. Kepler 62f is slightly smaller. Both are believed to be warm water worlds, possibly covered almost entirely by oceans, with scattered islands breaking the surface. If land exists there, it may be rare, isolated fragments of rock surrounded by endless sea. A world of archipelagos, paradise to some, horror to others. But water worlds near habitable temperatures are powerful candidates for life. Shallow seas, hydrothermal activity, constant chemical mixing, these are engines of biology. The problem is what we don't know. Surface composition, ocean chemistry, atmospheric density. Are these planets gentle cradles for life, or quiet, sterile mirrors of Gliese 1214b? Right now they are data points, numbers, spectral signatures, shadows passing in front of distant stars. And that is the cruelest part of this entire search. These planets may be alive right now. Not metaphorically, literally. They may host ecosystems that have existed for billions of years, longer than life on Earth. And we may never know, not because they don't exist, but because the universe is vast and we are small. And yet, the search continues, because somewhere among these worlds, hostile, alien, beautiful, terrifying, may be proof that Earth is not a miracle, but a pattern. And patterns, once discovered, never stay lonely for long. By the time you reach this point, one truth should be painfully clear. The universe is not designed with comfort in mind. It does not care whether a world burns, freezes, shatters, or quietly suffocates under its own oceans. Planets are not built for life. Life survives on planets despite that fact. And yet, despite everything, the glass rain, the molten iron storms, the crushing gravity, the endless darkness, life happened here, on Earth. That alone changes how you look at everything that came before. So far, astronomers have confirmed more than 4,000 exoplanets. That number keeps climbing. Every year, new worlds are added to the catalog, hotter, colder, denser, stranger than anything imagined a century ago. Most of them are hostile. Many of them are outright lethal. Some of them seem designed to erase matter itself. But buried among these nightmares are planets that sit in a narrow, fragile middle ground. Worlds that are not perfect but stable. Worlds that are not identical to Earth but better suited for longevity. Worlds where time itself is generous. That is what makes the concept of superhabitable planets so unsettling. They force an uncomfortable question. What if Earth is not the best the universe can do? Our planet is noisy, unstable, violent. Mass extinctions reset life again and again. Climate swings wildly. Asteroid impacts, volcanic winters, radiation spikes. All reminders that Earth barely holds itself together. Life here is resilient, but it survives in spite of constant disruption. Now imagine a planet with fewer catastrophes, thicker atmosphere, stronger gravity, more evenly distributed land and sea. A parent star that burns calmly for tens of billions of years instead of racing toward burnout. On such worlds, evolution would not need to rush. Intelligence would not need to claw its way up from extinction over and over again. Complexity could develop slowly, methodically, with patience measured in cosmic epochs. And that thought should make you uneasy, because if those planets exist, and the data suggests they do, then life elsewhere might not be rare. It might not even be fragile. It could be common, ancient, and unimaginably different from us. But here is the catch: distance. Every planet mentioned, every ocean world, every molten hellscape, every superhabitable paradise is separated from us by hundreds, thousands, sometimes tens of thousands of light years. These are not places we can visit. Not with rockets. Not with probes. Not even with optimistic science fiction timelines. Right now, they are shadows. Tiny dips in starlight. Chemical fingerprints stretched thin across space. We do not see their skies. We do not hear their storms. We do not know what swims in their oceans or crawls across their continents, if anything does at all. We are looking at them as they were hundreds or thousands of years ago. Some of them may already be gone. Others may be changing in ways we will never witness. And that leads to the final, quiet realization. The universe is not hiding life from us out of cruelty. It is hiding it because space is vast and we are young. We have been listening for only a cosmic heartbeat. We have explored only our immediate neighborhood. And already we have found worlds that shatter intuition, rewrite physics textbooks, and challenge the idea that Earth is special. Whether life exists elsewhere remains unanswered. But one thing is certain: the conditions for it are everywhere, sometimes violently wrong, sometimes eerily right. For now, Earth remains the only confirmed cradle of life. The only place where molecules organize themselves into curiosity, fear, hope, and imagination. The only place where beings looked up at the night sky and wondered if they were alone. And until we find another answer, if we ever do, that fragile blue world remains our anchor in a universe that is far stranger than we ever expected. The search continues. The silence remains. And somewhere far beyond our reach, a planet may already know the answer.